Hi guys, welcome to Learn Electronics Repair. We've seen this before, so this is a charger from a e-bike. This is the battery, e-bike or e-scooter anyway. I'll link the other video, but what we have is a chip somewhere on here, TEA1775. Oh, that one, the one with the hole in, yeah, the one with the hole in. So we have that chip with a big hole in it, and it doesn't work. I have the parts here now. They've actually been here a little while, and then as happens, I get busy and I forgot about this thing altogether. And then Detlef reminded me, because he actually was the guy who brought it in, and said, can you fix that thing? So we have some parts. This chip is the controller for the switch mode power supply. So as a reminder, this is the power supply. The mains comes in here. We have the filter, inductors, capacitor. Yeah, there's a fuse over there. Some more capacitors. And then we have, obviously, bridge rectifier. These are the switching MOSFETs on this one. This is a large smoothing capacitor. This is, I think, as I remember, it was some time ago, I think this is a PFC. So this is an inductor, there's another transistor there. I'd have to remind myself. And this chip controls this lot, okay? That one. If we look at the data sheet for this chip, it'll probably remind us of what we actually have here. Yes, this thing, guys. So it is, in fact, a flyback controller. That's effectively a switch mode power supply with integrated PFC controller. So this, in fact, does have PFC plus the power supply. That's a block diagram of the chip itself. Pinout. And a basic diagram. So this is, yeah, this is the PFC section. This is your booster, basically. Okay. And this is the output section. There, another MOSFET, and I remember a little bit now how this was, so we'll go back to the PCB. Okay, so as I recall now, these two MOSFETs are different. They're not the same as each other, they're not a pair, and one of these controls the PFC and the other one controls the main power supply. Yeah, and that was doing something else. I think I decided that this transistor has something to do with the startup circuit. Okay, what we'll do is we'll take the old chip off. I want to test all the main semiconductors. Let's have a good look for anything like burnt resistors, and if we don't see any, let's connect the light bulb in series with this and let's power it up and see what happens. I bought 5 of the chips. They are from AliExpress. I'm hoping these are genuine. Normally things like this are genuine. It's some big MOSFETs and such like that can be a bit fake-ish in my experience. So let's take the old chip off first and let's have another look around this to make sure we can't find any other obvious problems. I think I'll do this using hot air. I might try to get this off without the hot air if it's possible, but I don't want to damage the PCB, of course. I'm sure I will work out the best way, or at least a way. Whether it's the best is open to conjecture. So first of all, I'm going to add some flux. I'm going to try to get this conformal coating off, not like using something like ISO. We're just using heat from the soldering iron and flux. Let's see if it will come off this area or not. Okay. This coating, of course, this is the work of the devil, yeah. It's Satan's own work. I could get my big chunky soldering iron in here, but I'll probably try the other one first. So I'm using this more and more now. This is the C210 with this bent conical tip. I'm finding it rather good to use. It's set at 380C. Okay. Some solder on there. So I think we can say that coating is coming off quite well. I want to get plenty of solder on. This will help a great deal if I use hot air. Right. If I had 3 hands or a willing helper with 2 soldering irons, I might actually get us off. But if I just get the whole thing very warm first on this chip, obviously the chip isn't a good one. Yeah, we can see that. You can see it's bad. Which way round does it go, by the way? I'm just looking to see if there's any. Yeah, there's a dot, so we know where pin 1 is. And then I'm going to get hot air, and I should just be able to get us off then. The thing will be so warm it should just come off the board, I think. Okay. Right. It might be glued on, of course, just to make life difficult. This would not surprise me. Yeah. Okay, that's not coming off as easily as I would hope. It's quite possible we have some glue under this. Ah, I didn't want that to happen. It's just still so hot. Okay. That was not what I really wanted, but let's go. I didn't want that to happen because I don't want to lift any tracks off the board, but let's see. It's off. And I think we got away with it. Yeah, and this is the glue here and here, okay? Right. Well, we may as well clean that up while we're here. And I'm going to use the flat tip on this, the BC3. It's very good for this job. Okay. Same temperature, 380C. T12 BC3 tip. Okay. Right, well, we got away with it, guys. Let's clean that up. We can see the glue then that was holding this down. We can also see I actually did a very good job of that, probably as much by luck as judgment. I think I got so much heat in with the soldering iron that enough got through to soften this glue up. Yeah. With hot air alone, I think you would probably have damaged the PCB with that, so maybe that's the technique to think about. I'll certainly be using that again. Comments, guys? Yeah. While we're here then, with this removed, let's just check all the major components. In fact, let's try to check everything. So we see resistors, semiconductors, possibly transistors, where it says D, so it's probably a diode. Okay. D again, diode. We have the 2 MOSFETs. I'm confident I had these tested on the first video. And we have the power transistor. Okay, so let's do this, and then if we don't see any problems, we'll power it up with a light bulb. We might as well start on this side. So just ohms range first. These are low value resistors. Okay, look like 1, 0, and then silver. So this is like 10 times 0.01, which is 1 ohm, I think these will be. And it looks like they're in parallel, so probably read half an ohm here. Yeah, 0.5, that's okay. What else do we have here? Well, we have a couple of diodes, so diode mode. Looks okay. Looks okay. You don't really need to read on the other direction. If it gets a diode junction, it's not short, it's not open. And there's not much else that can be wrong with a diode, okay? The capacitors, unless they look burnt, I doubt very much would be short. This big capacitor just looks fine to me. I think sometimes a visual check is enough. We have two large diodes here, which we probably have to read from the other side. They're in parallel, it looks like it. Yeah, and I read a diode junction. What else do I have? Transistor here, which that's 2SC3852. That's going to be an NPN transistor. All these that start with C are NPN, A are PNP. Okay. I'm not sure if there's a mnemonic for that. I just know it. So we see base collector, base emitter. Looks like a transistor to me. And there's no short from the collector to the emitter, so that seems okay. Anything else on this side? Another capacitor. There's a couple little components down here. This is connected to the opto isolator. 393, 39K. You should learn to read resistor markings, guys, and colour codes. It's just much faster than looking them up. You will save a lot of time if you actually take the effort to learn them, yeah. And that reads 39K. Another power resistor here, we'll do that from the other side again. Inductor here, that should read short. These rarely go open, but well, we can test it. So the inductor is here, should read short. It does. The resistor here is another low value one. Reads 0.7. What is the value of that thing? Brown, black, silver. This is what I'm saying about learning these color codes, because if you then have to put those codes into a calculator, that's 5 times as long, maybe 10 times, okay? The MOSFETs, well, on a power MOSFET, you can say this is always the gate. Drain source or source drain, could be either way round. There is an S there, so possibly source. If we go gate to source, gate to drain, we might see a resistor on gate source. That just reads negative. That tells me there's a charge and a capacitor somewhere on here. When it reads negative resistances like that. Yeah, 46K. You'd often find a resistor, something like that, from the gate to the source or the drain. 1K. Yeah, 637K. You can't really see what these exactly should be. What you can say, if we go into diode mode, that between the drain and source, we should see a parasitic diode in one direction. There's a diode. And that reads high, okay. There's another diode. And that reads higher, okay. I'm happy enough with those. Reads okay. Fuse reads okay, that's good. Because I don't have any of that size, I'm sure I can fit something in. This RT, this is a thermistor, negative temperature coefficient. So this starts to highish, well, probably tens of ohms, and then goes down to a very low resistance. That we should check. These things tend to go open circuit, normally visibly failing, but who knows exactly. So this we will check. That reads like a short. Okay, we're on diode mode. Let's go to resistance mode instead. 3.3 ohms, okay, and in fact it actually says on it 3035, that probably is the value of it, so that's okay. Right, you can skip some of this, guys, if you want to, but it's probably important. Yeah, so we're going to work our way across the board now, just this way on the surface mount stuff, and see what we can see. I think what I'll probably do is I'll go over once looking for semiconductor junctions, and then again looking for resistors, okay? So that saves me continually changing from diode mode to resistance mode. probably quicker this way. So, any diodes? Capacitor shouldn't read short, by the way. Whenever you see a capacitor, it shouldn't, you'll know for certain it should not read short, unless it's across an inductor for some strange reason, okay? So I'm just looking amongst all this lot, another capacitor. Should not read short, doesn't. Diodes, so there's one here. The stripe will be the cathode, so you think red lead to here. Read 703. Now notice it's a Zener diode, DZ4. A bit over 7 is what you'd expect, forward biased on a Zener diode rather than 0.5 or 0.6 for a normal one. Okay, so that is what you'd expect on that one. That tells me that is a good Zener. Another one here. This is D, so this is a diode. 0.48, that's standard for a diode. Another capacitor. Oh, this is interesting. This reads short here. Ah, but look where we are. We're directly across a winding on this transformer. Do you see it there? We have a winding on the transformer, I would think probably from both ends. Actually, I'm not totally sure. I'm a bit suspect of that. Okay, we'll come back to that in a little bit. So, who else do we have? That's the Zener. Lots more capacitors. I'm just making sure there's no shorts across them. I'm not really bothered what I see. Otherwise, I just want to make sure it's not short across it. Okay. This says D52. This could be a double diode, common cathode or common anode, or it could just be a single diode. You would have to look up the SMD code, A4W, and see if you could find out. But if I see at least one, in fact, if you look, actually, look, it's in parallel. You see there's a bridge and the track just there. So this probably is two diodes in parallel. And it reads short. So we have a problem there with D. Well, actually, it's DS2. That maybe not be a diode. But it looks suspicious to me. Okay, we'll come back to that one. DZ, so we'd expect about 0.7. Yeah, 0.717. A normal diode, 0.4, 0.5, 0.481. Good. Another one, good. 0.585. Between 0.45 and 0.6 is about right for a silicon rectifier diode. So that's all we have, and this looks suspicious. And that looks suspicious. Okay, now let's do the resistors. Another capacitor here, by the way. Okay, now resistor. Sometimes with the resistors you can't get an exact reading in circuit. They should read at least the value or lower. So this one here now, 1, 2, 3. Okay, it's not 123. It's 1, 2 and 3 zeros, which is 12k. And this is what you need to learn. Yeah, it reads 11.97. 102, 1 0 and 2 zeros. 1000, 1k. Reads 1k. You see why you need to learn them, guys? 473. You know, 4, 7 and 3 zeros, 47k. That reads considerably lower, but to be honest, a lower reading is generally okay. Resistors like this do not fail by going low in resistance, unless they go short. And they probably don't, they just burn up actually. They normally go open. It's very rare for a resistor to actually go short. In fact, I would say probably impossible, but okay, who knows. 435. These are high value, and you see, are they in parallel? No, they're in series. This will be part of the startup circuit. That's why we have such high value resistors. 4, 3 and 5 zeros. Okay, so that's a 4.3 mega ohm. That's the same. So these are going to read very high. They shouldn't read higher than the value. And that reads very high, 20. That is quite possibly faulty. They should not read higher. What's this one read? It's quite possibly that's open circuit. You see that negative reading? That suggests the capacitor's got a bit of charging. Probably from my multimeter. 39 meg. Those are extremely suspect. In fact, I'd say they are faulty. These we need to come back to. Okay. This. Oh! Okay, this mystery I've solved. This is not a capacitor. I didn't spot it before. Probably you guys did. This is an inductor, L7. And that would read basically 0. And it does. So that reads okay in actual fact. And the other suspicious thing is this DS2. The fact it says DS tells me that's not just a diode, it's something. Okay. Back to the resistors. We have a 47k. Yeah, great. 15k, 3 of them in series, 4 of them in series in fact. Reads 15, 30. In fact, you can say end to end, it should read 60. 15, 30, 45, 60. Yeah, 60k. How about that? All checked at once. Just by keeping my eyes open. Low value resistors. 3.3. Reads 4. That's good. That's close enough. 3.9. Another one. Same. They're in series. Look. 7. That's pretty much spot on. What else do we have? 821, 820 ohm. 820. 0.824 of a K, that's 824 ohms. What's this thing? 914. That is a standard value, so that's 910K. A bit less than 1 meg. Reads 1.9 meg. Let me see. That I think reads too high. And notice this is connected with these. Can you see that? That is reading too high. The meter's gone a bit crazy. Sometimes it does that. Let's get back. I think what's happening when it does this is it's like turning on a semiconductor somewhere and turning back off again. But that reads 1.9 meg. That is too high. And it's part of this circuit. You can see it, can't you? So the current which is damaged those will also damage this one. That goes to another one which is 15k. Maybe this is also bad. That's actually okay. So another one. I'm going to measure these with a different multimeter than me, just to be sure, okay? The fact we have all these high value resistors reading bad. 820 ohms we've done. 0. Good enough. 1k. Good. Yeah, good. These are more these 4.3 meg. Can't get a sensible reading on it. 7.2. I'm now beginning to suspect there's a problem with my meter reading these very high value resistors. I can't imagine they were all actually faulty. Doesn't kind of like weigh up to me. 470k. Also reads bad. Right. I've seen this sort of problem before, but that, especially that flicking backwards and forwards. The multimeter is on auto, and I've now put it onto manual ranging. So you can see, if I press the button, we're on ohms, kilo ohms, it's moving the decimal point, kilo ohms, mega ohms, mega ohms. Okay, so we're on the high range of mega ohms. Now let's read these all again. Still reads open. Still reads open that way, but I'm getting different reading the other way. 910k. No, these are still reading bad. All right, okay. Let's look at these ones. Reads open. I still don't trust that. I'll leave this on auto. Let's see what this tells me. Okay, this is telling me the same, 7.3. Same crazy behavior. You see it flicking between the ranges? .7, 5.8, 5.7, 5, no, about the same, 470k, reads 600 and something k. Oh, let's continue. Okay, 913, 91k, reads 88, that's very close. This one 68k. Yeah. This one 56k. Yeah. This one 470k. Yeah. 0.467 of a meg. 33k. Yep. 39k. Yes. 5.6k. Yes. What is that? That is a resistor with a hole in it, I would say. Yep. And that looks like, well, it goes to this chip on here, which is pin 14. We might be able to figure out what that is based on what that pin is. Okay, so that is bad. What else? So 3.3 ohms. Yeah, close enough. 47 ohms, not 470 notice, 47 and no zeros. 47 ohms. Okay. And I think there's one more here, 5.1 kilo ohms, and a 27k. Right. So what I have appears to be a lot of open circuit or high value resistors here. So this area is coming from the high voltage. We can sort of see that it's in the high voltage circuit. These are very high value resistors. I'm not 100% convinced my multimeter is even reading these correctly, but that's what they are. But if they are open circuit and such high value resistors, this is something to do with the startup for the chip. And the chip will have a startup supply for the PFC and a startup supply for the switch mode or pulse width modulator control, okay? And I think that's what these two things are. And if these resistors are faulty, what's going to happen is that the chip never starts. Okay, it just won't start. It's not going to go bang, it ain't going to start. So for now, I don't think we need to worry about them. Because there's a lot of high voltage here, I'm going to just clean this white pen off before I start. I don't think this stuff is conductive, but this is high voltage circuitry, okay? What's more to the point is this. Now, this one, DS2, I think is probably a Schottky diode, or supposed to be. I'm going to get this white ink off again just so I can see a little bit more around here, but I think that might be connected to that, and we need to look at the data sheet to see what pin 16 is on this chip, and that may tell us something about this resistor. And also, as I tilt it, I might be able to see some marking on it. Okay, so this resistor is a green one. I will try and clear this off it to see if I can see any sort of sense of that marking. I can just see the bottom edge of it. We see a 3R3, we see a 47, we see a 27K, all in these green ones. What does it actually read? Well, it reads open, so I'm sure that has failed. So can we read anything from that? Not really, but we know where it goes to. And the other thing is this A4W. So let's see if we can find what that is. But I'm thinking probably Schottky diode, okay? So, data sheet. I can see that pin 16 is the HV connection, and that effectively connects to the main smoothing capacitor here, C bulk. So, that pin, we can have a look. High voltage startup and flyback valley sensing. I don't know if that's going to be a particularly low value resistor. It could be. Okay. According to our typical configuration, this connects directly to here with no resistor. So I think that's going to be a low value resistor. I would probably go on the basis that if they've put other low value resistors in here and they were like 3.3 ohms or something, green ones, I'm going to put the same. What do you guys think? Let me know what you think of that, but that's my, what else do I have to go on, basically, yeah. This, possibly Schottky diode. A4W. SMD code. What does that find as well? There's a picture of some, and these are diodes. Oh, A4W. I have these. This is a Schottky diode, I think. Look, same package, SOT23. I'm pretty certain I have these. So that we can change. Yeah, this is saying A4. Have these diodes, BAV70, A4. I'm really not sure what the difference with the W is, but hey, we can stick one in and find out. So we have something for that. And we can say that is short. Or it's wired across. Oh, hold on a second. Is this wired across this 47 ohm resistor? It looks like it is, and that would make it read a very low resistance in diode mode. Okay. Let's look. Yeah, it reads 036. If I go into ohms range, I bet it reads 47 ohms. Yeah, how about that? So I don't think that's faulty at all. I would have to remove the resistor to read the Schottky diode, but if it is faulty, it's just open. Okay, but to me, I think I have enough evidence there to tell me that's almost certainly okay as well. So what we're going to do, we're going to replace this chip. We're going to put a low value resistor in here. We're not going to worry about that lot too much at the moment, and we're going to see if it works. Let's have a look at these high value resistors under the microscope as well. So we can see we have two of them here. 4.3 mega ohms. And that actually reads 2.5 now. That also 2.2. So they're not in parallel, but they read very similar. And they can read lower, as I always mention. 914, 910K. That read, yeah, 850k. So you see now that these are actually reading. I think what was happening is one of the ceramic capacitors had a bit of charge in it, and because I'm measuring extremely high value resistors, that reads 2.93, it was just completely confusing the multimeter, and not just the fluke meter, but you saw that the other meter, the high reads, had the same sort of problem with it. 470k, 466k, yeah, they actually read all right now. So I'll clean all this off here. I'm happy at the moment with those. I'll fit a new chip. I honestly can't read that, guys. I'm gonna fit a fairly low value resistor in there. According to the typical application, it doesn't even need a resistor there. It just connects directly, and let's see what this thing does. The diode, Schottky, I'm quite happy with it. We know what we're going to do with this, so let's do it. I'll take this resistor off first. Bit of heat into both sides. Hopefully this will come off with just the one soldering iron. We can try using two. We could use hot air, but it seems a bit overkill for this. Yeah, you see how easy that was. Okay, a bit of flux would have helped as well, of course. We can do that to clean it up. There's the original one, upside down. I only want to know what the size is. So this is a 0805. I'm going to put a 4.7. Another good reason to expect this was a low value resistor is because this is obviously failed when this chip went short or blew up. If it was a high value resistor, it wouldn't have burnt up, yeah, because no current flowing through it. If it was a high value resistor, it would handle a high voltage drop across it. Don't be afraid of this sort of thing. At the end of the day, guys, you've just got to make a judgment call. There's nothing else you can do. Maybe the guy's got another one of these. I've got some more chips. If it blows up again, I might just ask him, but for now, I think the judgment call is a pretty good one. Okay. I'm doing this left-handed without any stereoscopic vision. Okay. It might have been something like a 4.7. Don't see why it couldn't have been. I'll just hold that down so it doesn't wander off. Like so. Okay. I slipped. Look at that. Yeah. Just because I wanted to do the other side, I slipped. It's alright. I'm not being OCD today. I'm not too worried if it's a little bit ski whiff. Okay. Let's get the chip on and then we'll clean this up. So much the same technique. I'm going to get the chip in my right hand. I can see where the dot is over here. So I'm going to, let's think which is the best way for me to do it now, the best angle. I think I'm going to come in at it in this direction. Okay. Let's try that little C210 again. I've been used to using the BC3 a lot for this sort of work, but I'm starting to like this little thing. This was a free sample, by the way. It's a Sugon T26D. I made a review with this one. The T12 is actually my own. I bought that myself a few years before I had the YouTube channel. Okay. This won't go AWOL because the heat won't get through to that end like it would with the resistor, so that's why I didn't bother to hold that down. Okay, bit of flux, yeah, just a little bit more solder, then we'll try to drag the soldering iron down. This is quite nice with one of these bent conical tips. Add a little bit of solder as we go. So I have a solder bridge there. See how I picked it up? Moved it to here, okay. Let's see. Yeah, that was pretty good. Turn it the other way around. It's just easier for me in this direction. Okay, again, solder bridge, take it off. Yeah, this bent conical is quite nice actually. I rather like this. Okay. That's pretty good, guys, yeah. Slightly crooked resistor. You can chastise me if you wish down there. Am I bothered? No. Okay. Chip's nicely fitted. I should put some varnish or coating back on this. Clear nail varnish is actually very good. I'll see what the wife's got. Perhaps just try and get some of that, okay. Right, let's power this up and let's see if it actually works. So the first and probably most important question is, will it explode? Will it explode? We'll give ourselves the best chance, so let's put the current limiter in. Yeah, remember to switch the current limiter into circuit, yeah. I never forget to do that, guys. Honestly, I've never forgotten to do that, yeah. Believe that, you'll believe anything. Okay. So, that bulb should come on bright and then go dim. I don't think it's going to pulse because there's no load on this. It might pulse if we have PFC. Otherwise, if it comes on bright and stays bright, something is not right. And if something explodes, then something definitely isn't right. Okay, so camera running, what does it do? Well, you see, came and then it flicked. So the flick, I think, was a PFC firing up. It's not going to explode, this is for sure. I think I might have heard a relay click when I did that as well. Which is strange because I don't actually see relay on here anywhere. Okay. Yeah, let's have a look to see what voltage we have coming out of this. I'm just trying to position this somewhere so that this doesn't short that neutral wire. Okay, so get the multimeter and let's see if we can see anything coming out. I don't like the way that keeps sliding this way, so I've put a pen there. Just something to dissuade it from doing that, I hope. Okay. Right, so DC volts. I'm sure that's the output. What does it do? Well, we got a little bit of voltage and then it went away, but that could well be normal. This is a charger after all. Okay. Here is a battery. What this thing is, BTE6010, upside down for you guys. 36 volt battery, 11.6 amp hours. Okay, again, get the meter across that. I've switched the current limiter off now. We're on direct mains because we've now got a load. Okay, what does it do? Oh, well, something went pop. That's what it did. Did you hear that? Something went pop. Something went pop. Well, let's go back to the current limiting light bulb again. Let's watch that again. And now it doesn't light up. Okay, we have a large capacitor on here which could have some high voltage in it, maybe. It's over here. That has 300 volts in it. Can you see that? $305 volts in it. Well, back to the drawing board, guys. If you think about it, this is quite interesting, actually, because the fuse is blown, we can see that. It is working. fuse has blown, okay, but the large capacitor, the big bulk capacitor, had like 300 volts in it. So if there's a short in this circuit, the capacitor would discharge, yeah? But something's obviously caused a big surge of current because the fuse is blown. So like the two factors kind of like are a bit, how could I put it, they don't quite match each other, yeah? They don't coincide. I'm sure there's a better word, yeah. So I've got a good idea what actually happened to this because the facts tell me so. Let me show you what I think's happened and then we'll have a look. Here is the typical configuration. So my circuit is going to be very similar to this, okay? Now, the fuse basically is here somewhere. Mains in, okay? Fuse is here somewhere. The large capacitor is here. So the fuse is gone, but the large capacitor holds a voltage charge. Now, if there was a short somewhere in this, like the MOSFET or something, or the chip, then the capacitor would be discharged. Yeah? So that leaves two possibilities. One, that there's a short somewhere on the output, so effectively it puts a massive load on this. The more current the output draws, the more current the primary or input circuit has to put in, and that can blow the fuse. Or there's another possibility. You see here, this is the PFC MOSFET. Now, there's a diode here, and if this goes short, PFC, that will blow the fuse, maybe blow the rectifier as well, but it won't discharge this capacitor because this diode is now reverse biased. So this can stay charged up even if there's a short on this side. So we could have a short somewhere in this side. Now the other thing you would think is, if this capacitor is charged up, why doesn't this chip just keep on running? Okay, just keep on running until it drains the capacitor. Because for that to stay charged, this must have stopped. It must have stopped switching the MOSFET. Now, I think the most likely reason for that can be explained here, V-sense. So this is sensing the input AC. Yeah, you can see there. It has a sense, and it's sensing the input voltage. And if we look to see what that does, it's probably involved with this under voltage lockout. So effectively, if the supply voltage is too low, this stops running. And obviously if the fuse is blown, even if that's fully charged, the input voltage is too low, it should stop running, okay? So I'm sure that would explain, and also there's a sense input for the PFC output voltage as well, why this can stop running even though that capacitor has a high voltage charge. Okay, so let's have a look to see if we have a short on the output or the input side. And I'm thinking we may not find one. Let's see though. I could be wrong. I often am. So the PFC MOSFET is one of these two. I did work out on the first video which one it was. I'm probably able to do that fairly quickly again. We can see that this one goes up into this thing here. You see where it goes to? And that is the PFC choke, because this is the transformer. So this will go up into that transformer somewhere. It heads that way. I'm happy with that. So this is the one. Has it gone short? This is going to be the gate on this end. So gate, source, drain, whichever way round. No, it has not gone short. That reads like a diode. Oh, this does read bad. Yeah, this doesn't read right. There's low resistances here. Oh, maybe that is short then. PFC went short. This one, I'm sure it's open because the capacitor didn't drain. That's the parasitic diode we see in the reverse direction. Remember, the drain is positive to the source. So in that direction we don't see anything. In the other direction we see the parasitic diode, which is an internal feature of the MOSFET, okay? So it looks like it's not exactly short, but it reads low. Okay, we can take that out and check it. The other place to look for shorts would be on the output of here, okay? that's just climbing up. Which is polarity is it? Yeah, this is the positive. Okay, it's just going up. There'll be a capacitor on here charging somewhere. Okay, so we don't have a short on the output. It's possible we have a short circuit battery, because if you remember, I'm sure you do, I first tried it powered up okay, I attached the battery and it blew up, but not instantly. I really don't know how to measure, or I don't have the equipment to measure the internal resistance of the battery, unfortunately. I can connect and see if it's short. No, it's not short and it reads a fairly high resistance. Doesn't mean it effectively isn't going short when it tries to charge. But it looks like it's at least not short. So, okay, well, the theory worked out where I said the short would be. It turns out it was the one I said out of those, I don't think it was, but it is. So let's get this MOSFET out. And let's see if it's okay, because that's a bit of a strange reading. I think you'll agree. Let's just go to ohms range. Yeah, about half a kilo ohm, 450 ohms. I'll just check the bridge rectifier as well, because obviously the current that blew the fuse also flowed through here into there, so this could also be faulty. Okay, that reads like a diode. That reads like a diode. And then from the positive to the AC, reads like a diode, reads like a diode, and this should read, well, we've got that 206. That I think is that MOSFET. Okay, let's see. Yep, there we go. So we do have a DUF MOSFET there, PFC MOSFET. That is the part number. I do not have these in stock, unfortunately. I have more of the controller chips which is connected to this, so that in itself isn't a problem. I bought 5, I have 4 left. If we just look, the chip itself looks intact, although I would probably change that because the MOSFET went. The resistor that I fitted, that I was discussing what value it should be, this one, 4R7. Reads good, and it doesn't look distressed, so that I think was a perfectly good guess. Why did it fail? I would suggest 2 possibilities here. One, that this MOSFET was effectively a walking wounded from the first failure when this exploded. This MOSFET could have been stressed, damaged internally, but not fail. And then once we put a load on the thing, it fails. It's possible. Okay, it's quite possible. It's also quite possible that the MOSFET, the PFC on this, only fires up once there's a load, because if you haven't got a load, you don't need the PFC. And for the sake of efficiency, I haven't looked at the full data sheet, but it's quite conceivable that the PFC section comes on when it needs it, i.e. when there's a load. The other possibility is that the battery itself is faulty and the battery blew the power supply up. I think both of those scenarios would explain what we saw. The power supply fired up okay, I put the battery on and it blew up. Okay guys, so can't fix it at the moment, but I think we learned a hell of a lot, don't you? Okay, I'll get some MOSFETs ordered and we'll have a look, and I'll see if the guy can either test this battery on another charger. If it blows up, I know it's faulty, or can bring me another battery when I've got some MOSFETs here. Okay, hope you enjoyed that. Please get into the comments below what to discuss I think about this repair. So I really do look forward to hearing from you, and I also look forward to seeing you all soon on another Learning Electronics repair video. Ciao for now, guys.